Can everyone hear me? All right, thank you very much. I'm going to be talking about a paper I wrote recently with Andrea Caputo, who should be around here someplace, as well as Carlos Peñagaray. And if I have time at the end, I may also comment on ongoing work that I have with Andrea, Carlos, as well as Marco Tauzo, Marco Regis, Jorge Varela, and Jorge Salvador. And the title I originally proposed for this talk was Searching for the Decay of Axion Dark Matter. Although I realized on Monday while I was preparing the talk that this was a little misleading and suggested that I would be doing some searching. I prefer to work from a chair usually, and so I decided to change this at the last minute to showing that the decay of QCD axion dark matter is not hopelessly invisible. And I have three sort of main goals that I'm going to try and convey in this talk. The first is more or less maybe obvious to many of you, maybe not depending on what you work on, and it's that radio telescopes often offer a very unique probe of QCD dark matter. From an astrophysical perspective, they are ideal to look for dark matter distribution in galaxies. The second one is that on large galactic scales, the decay of axion dark matter to 2 photons, which the decay process I'm going to be emphasizing in this talk, is far more dominant than the conventional considered photon to axion or axion to photon conversion, the Primakov effect. And lastly, I'll go through some sensitivity analysis, in particular for the square kilometer array, to see what sort of sensitivity we can actually gain to the axion decay, and I'll try to convince you that there may be hope potentially starting to probe the edge of the QCD axion band. Alright, so we've had so many talks on axions. I have an obligatory slide on this, but I'm just going to skip this because we all know why we study axions, why they're important to solve the strong CP problem, why they provide a very interesting dark matter candidate. You know, of course, everyone knows that there's a straightforward relation between the mass of the axion and the Pecha-Quinn symmetry break scale, and you can write down your conventional Lagrangian that contains the axion standard model interactions. And typically, people focus on this FF dual term because it provides very unique, strong signatures of the QCD axion. And this is the term I will focus on as well. Typically, people are focusing on the Primakov or inverse Primakov effect. This is what people do when they look for use helioscopes or helioscopes, as well as the indirect talk that was given yesterday by Ben Safdie. Today, I'm going to talk about this other process, the straightforward decay to 2 monoclinic photons. All right. So I want to set the stage a little bit. Why nobody really spends a lot of time talking about the straightforward decay process. If you consider the historical perspective of this, the original Pecha-Quinn Weinberg-Wilczek model said the Pecha-Quinn symmetry breaking scale to be roughly speaking the electron-weak scale, and this applied to 200 keV axion mass. Now, this was immediately ruled out, and people had to get more creative with how they solved the strong CP problem. And what they did was they pushed the Pecha-Quinn symmetry breaking scale up with minor model modifications, and in doing so, pushed the mass of the axion down. And if you look at Lagrangian, you see that the axion interactions with FF dual become increasingly suppressed as you do this, and so the axion effectively became invisible. Now, at a certain point, you reach a mass of about 20 eV, and you can calculate the lifetime, and you can find that at about 20 eV, the axion becomes, lifetime of the axion becomes longer than the age of the universe. Now, the axion lifetime scales like ma to the minus 5, so for every order of magnitude of mass you go below that, you start increasing the age significantly. And you can now sort of take the benchmark model. You can say, I'm going to be interested in a 10 to the minus 4 eV mass, which I'll justify momentarily. And you can take something like a KSVZ type coupling of 10 to the minus 14 inverse GeV, and you can see that the lifetime is 10 to 45 seconds. Now, that's a huge, huge lifetime. And you may sit there and think to yourself, how are you ever going to probe that? Well, I don't like to work with big numbers. I prefer much smaller numbers. So allow me to just convert this to years. Makes me feel a little bit better about it, 10 to 37 years. And consider for a moment, something like super Kamiokande. We, with terrestrial experiments here on Earth, are able to put limits on proton decay of the order of 10 to 34 years. So if you compare these two numbers, it doesn't seem so ridiculous that we might be able to put astrophysical limits, given a large astrophysical environment, on a particle with a lifetime that's slightly larger than that. So while large, maybe it's worth investigating. I want to take a brief aside here to motivate what sort of mass range we're talking about. I told you a second ago that I was going to take this as a representative example, but there's reasons to consider very specific mass ranges, and this will come to the motivations for why we use radio telescopes. So if we require that the axion accounts for the entirety of the dark matter, what can we actually say about the mass of the axion? This has been discussed by one or two people at the conference so far, so again, I'll try and sort of rush through it. But there are two scenarios. The first is where the Pecha-Quinn symmetry is broken prior to inflation. Here you take a small patch of the universe, during inflation it inflates, and your relative density during the vacuum realignment mechanism is produced by essentially the initial condition on that patch of the universe that you inflated prior to inflation. Now you can say maybe I prefer values of theta I, where theta I ranges from 0 to 2 pi, that are something between 0.3 and 3. These seem like a reasonable order 1 number range. And if you do this, go through the calculation, you find that the mass of the axion that gives you the right relative density is something like 10 to the minus 6 to 10 to the minus 4 eV. Of course, you can push this value to higher values, which is 2 pi, and if you go up to 2 pi, the mass of the axion increases to something like 10 to the minus 3 eV, and you can go arbitrarily low towards 0, and in doing so, the mass of the axion drops. But again, something like 10 to the minus 6, 10 to the minus 3 EV benchmark might be something that you have in mind. Now, the alternative scenario, where the Petrov symmetry is broken after inflation, here you have the axion takes on random field values in small patches of the universe. So you can imagine performing some averaging procedure to calculate the contribution to the axion relative density from the vacuum realignment mechanism. People have done this in the past, and the number they come out with is, roughly speaking, something like 20 micro EV, so 10 to the minus 5 EV. You keep this as a benchmark number in your head. Now, these aren't the only contributions to the axion energy density. There's also the decays of topological defects, and this was discussed in Vincent's talk yesterday, or 2 days ago, I forget. Again, I'm not an expert on this, so I don't want to go through the estimations that people have made or spend too much time on this, but you can sort of take a general look at the numbers we obtain for the contributions from string decays, from string domain wall collapse, and the numbers you get tend to be between 10 to the minus 5 and a handful times 10 to the minus 4. So again, a benchmark seems to be, roughly speaking, 10 to the minus 5, 10 to the minus 6, 10 to the minus 4, 10 to the minus 3, if you want to be a little more extreme. So let's put this together in a plot of the axion mass. Below 10 to the minus 6, you either overclose the universe, or you have to justify your small initial condition somehow, either through anthropic reasoning or however you like it. If you're sitting above 10 to the minus 3, you start to run into problems with astrophysics. You either prevent helium burning in stars, or you have an issue with supernova 1987A. Now, if you take the mass of the axion and you just convert it blindly into a photon energy, you find that you're lying between 240 megahertz and 240 gigahertz. This is exactly the range of frequencies that radio telescopes are intended to probe. So you think to yourself, this seems to be an ideal way to look for somehow making the axion mass, rest mass, into a photon energy. And I've highlighted just a few radio telescopes. This is certainly not an exhaustive list. There's hundreds, not hundreds, but tens of more. You can see it on this list includes Green Bay Telescope and SKA, which were the 2 telescopes that were talked about yesterday during Ben's talk. Okay, so people have developed this idea of axion indirect detection. They thought about it a while ago. Actually, about 20 years ago, people at the haystack antenna tried to look for the decay of axion to 2 photons, and you can see they were actually able to set limits on the axion photon coupling of the order 10 to the minus 9 in the axion mass range of the 300 micro eV range. Now, it's a very, very small window, and there's many reasons for this, mostly limitations of the radio telescope they were using, but we've had 17 years to develop technology, to develop our understanding of astrophysics, and we've come a long way. So the questions we're asking here are, can we actually significantly improve the sensitivity to put competitive limits with terrestrial-based experiments? And to give you a perspective, this is the conventional plot we've seen a few times now, where we have the axion photon coupling on the y-axis and the axion mass on the x-axis. I've highlighted here in the red the range of masses that we're approximately trying to hit. And here the yellow dot is the limit that they were able to put in 2001, I think. Many experiments will come in the following years from, of course, MAGMAX, AMX, YAXO, all of these experiments. We'll continue to push down, but I'd like to show you that with our estimates, you may be able to gain a few orders of magnitude and sensitivity in exactly this region that we're working on with the QCD axion. All right, now there's been a renewed interest sort of in the indirect detection of axions recently. Last year, there was a paper looking for axion photon conversion in the Galactic Center by Kelly and Quinn. They made an initial estimate that they could clearly probe the QCD axion. Unfortunately, their calculation assumed that the magnetic field was homogeneous. And as you drop that assumption and actually adopt terminal magnetic fields, you find that the energy density centered around the k-space mode that you want to pick out for the axion photon conversion suppresses the estimation by something like 13 orders of magnitude. I'll talk about that a little more in a second. In that same paper that was discussed, there was a proposal to look at the stellar winds of Wolf-Rayet stars. Unfortunately, there's large uncertainties with the environment, so making firm predictions for the axion signal might be quite difficult. And of course, we heard talks, for example, yesterday of Ben Safdie on one of these papers, which were looking at axion conversion near neutron stars. So this seems to be an interest, topic that's garnering a little bit of interest these days. All right, I'm going to begin by talking about the Primakov effect on galactic scales. for non-relativistic axions at rest essentially. I want to make a comparison between this and axion decay for various environments, convince you that axion decay is indeed the relevant process. You can write down the flux density for the axion to photon conversion, which is nothing more than an integration over the axion density times this factor rho m, where rho m is capturing the magnetic field energy density centered around some k mode. And the k mode is going to correspond to the energy essentially of the axion at rest that we're looking for, or the photons that we're going to be picking out. Now, it was shown that for turbulent magnetic fields, you can characterize essentially the magnetic field energy density by two values, the RMS B field and the coherence length of the magnetic field. If you write down the magnetic field energy density like this with some suppression factor f sub k, which is less than or equal to 1, and you adopt some theory of turbulent magnetic fields, you find that you expect a power law for this function f sub k between a power law that suppresses the overall contribution to the energy density, like the k mode you're looking to, times the coherence length of the magnetic field. This minus 2/3 is simply from one model of magnetic turbulence. Of course, it's a little naive, but nevertheless, all models seem to adopt this power law suppression. Now, if you take an axion at rest, you find that, roughly speaking, the k values you're looking for are on a centimeter size length, and of course, coherence lengths of magnetic fields are on an order of parsec. So the mismatch between these two is gigantic, and this is where you get this huge, huge suppression factor from. Now, it doesn't matter whether it's 10 to the minus 13 or 10 to the minus 10 or 10 to the minus 8 or 10 to the minus 20. I'm going to show you in a second that even if it's about 10 to the minus 2, you're safe in most environments. But it's important to keep in mind that this is really the reason you're not looking for the Primakov effect in these lower scale environments. Now, from axion decay, you can write down the flux density arising from a spontaneous decay of an axion. And again, you have some density integral over the axion lifetime. But this isn't the end of the story here. This is the flux that you would get from an axion decaying in vacuum. But we are producing axions. We are allowing axions to decay not in vacuum, but actually in a background of photons with the exact same energy as we have from the as is produced in the decay of the axion. This leads to a stimulated emission enhancement factor. Now, the easiest way to see this is to consider the Boltzmann equation. If you write down the collision term of the Boltzmann equation, you find that the number density, change in number density, is equal to the conventional matrix element squared times two terms. The first term is the Na is the number density of axions, and N gamma the number density of photons, background photons, at an energy of half the axion mass. So for the first term, you have the eta gamma gamma enhancement of the phase space minus the N gamma gamma negative. And in the limit where N gamma is small, this leads to the number density of axions times 1 plus 2 N gamma. The factor of 1 is giving you the contribution of spontaneous decay, and the factor of 2N gamma is going to simulated emission. Now, this factor is something you always have. We're sitting here in the radio, we're sitting in the Rayleigh-Jeans tail of the CMB. So at the very least, we are guaranteed to have number density of photons coming from CMB background. Spatially uniform everywhere. Perfect. Now, also, I might comment later, depending on how much time I have, this factor can be enhanced significantly when you're sitting below a GeV. Above a GeV, the radio background is CMB. And below a GeV, you typically are talking about synchrotron emission. Synchrotron emission as low as order 100 MeV can be 3 to 4 orders of magnitude larger in flux than the CMB. And if that's the case, this can enhance your signal by many orders of magnitude. And it's already enhanced even without synchrotron by many orders of magnitude, even at low frequencies, significantly more so at low frequencies. So this is a really, really huge point that's going to boost our signal quite a bit. All right, now if you allow me, I'd like to make the naive comparison where I compare the rate of eta gamma gamma over eta gamma. I'm essentially just going to throw a cancellation on the density integral factors, even though the density integral from eta gamma gamma should be larger for geometric reasons. And I'm going to naively take Fa, the suppression factor, which I just told you could be of order 10 to the minus 13 to be 1. Of course, this is ridiculous, but just humor me. If I plot this ratio on the y-axis as a function of the axion mass on the x-axis, I can highlight various sort of magnetic field environments. This gray line on the right-hand side is an environment where the magnetic field is 10 to the 2 microgauss. The next line is 1 microgauss, 10 to the minus 2 microgauss, and 10 to the minus 4 microgauss. The dashed line across the center dictates where decay dominates versus where magnetic field conversion dominates. On the right-hand side of this plot, I've also highlighted various magnetic field strengths you can expect from different environments. So for the galactic center, you might expect a magnetic field strength ranging between 10 and 50 microgauss. For dwarf spheroidals, there are typically upper limits only on the magnetic field strength, limiting it to be about 1 microgauss. And then, of course, as you go lower, you can run into the intergalactic magnetic field strengths. And what you see is that for maybe a few times 10 to the minus 5 and 1 microgauss, axion decay begins to dominate. So for a large range of parameter space, with the suppression factor taken to be optimistically the maximal value allowed, you already expect to see the decay dominates. Now you throw in the realistic factor, and it becomes not so much of a comparison. Okay, so I hope that I've convinced you that radio telescopes are ideally situated to probe the decay or conversion of QCD axions. I hope that I've now shown you that on large galactic scales with turbulent magnetic fields, we don't need to be concerned with axion to proton conversion. We should be concerned about axion decay. Now I'd like to go through a brief sensitivity estimate, tell you what we want from our telescope, what we want from our environment, and what sort of sensitivity we can actually gain. Alright, for a radio telescope, we first want to make sure that we're actually probing the QCD axion. There are radio telescopes that go up to, say, 900 gigahertz. We don't need to go up to 900 gigahertz. There's no point in going there. Astrophysical balance will rule those out immediately. And there are many telescopes which go below 100 megahertz. This, again, is too low. We need the anthropic conditions. It's also further away from the QCD axion band, so from a projection standpoint, it sort of looks bleak. We also want to make sure that we can resolve a large number of channels. We're going to have a very narrow spectral line, where the width of the spectral line is set by the velocity of the dark matter and the objects we're looking at. So if you take something like a galactic center, you have a 300 kilometer per second expectation value for the velocity of the dark matter. This means a width of that over c, so 10 to the minus 3. We also want a large field of view. Radio telescopes are notoriously known for having very narrow fields of view. But if you have a large field of view, you can capture a larger dark matter column density, and so it stands to reason that you want something with a smaller dish size. Now, actually, that's not entirely true. There's some cancellations depending on what you want for signal in the background, but you want to make sure that your integration angle that you can gain from the dark matter column density is as large as possible. And lastly, you want something like a large signal of noise, so you want a low system temperature, low internal intrinsic noise temperature, and a large effective area. So SKA mid offers a lot of these features. We're probing frequencies in the range 350 megahertz to 20 gigahertz, which is sitting right in that range of something a few times 10 to the minus 6 eV to 2 times 10 to the minus 4 eV. It has fantastic spectral resolution. They have dedicated searches to molecular lines, and so they're expecting to get resolution on the order of kilohertz. They want to resolve objects moving at 1 kilometer per second in the galaxy. They have 13 and 15 meter dishes, and they have a phenomenal effective area to system temperature. And just to give you an idea, this is a future experiment, so it has not yet begun operating, but we're sitting here in 2018 between this basal construction sign, and you can see it turns on in 2020 and full operation in 2024. So, I told you earlier that in general the photon number density for evaluating the energies of half the axion mass is in general a linear combination of many terms. These can be quite complicated. You have to model the spatial distribution of synchrotron emission, because in general there's an integration over both the dark matter density, where the axions are decaying, with the background distribution of number density of photons. For the CMB it's easy, it's not a problem. But for synchrotron free, it becomes a little more complicated. Assumptions enter into your game. And if you want to make some sort of conservative flatline estimate, it's better to maybe avoid these as a first overall approximation. So we're going to look for environments where synchrotron free emission are extremely low, and we can take n gamma to be dictated exclusively by the CMB number density. Generically, this is always going to be true above a gigahertz, though. All right, small field of view means that we're roughly spanning less than an angular degree in the sky. So it doesn't mean it's not necessarily bad to look at distant objects or small objects. You're not going to necessarily always gain by going to the galactic center because of your small field of view. So keep that in mind. And of course, we have an astrophysical input that we need, an integration of the column density divided by the dispersion. So you can always make assumptions for this. I can always say I'm going to go to the galactic center and assume some NFW profile with these parameters. But actually, we've heard multiple discussions today on the derivations of density profiles and J factors from dwarfs. And a lot of the interest in WIMPs has led to a better understanding of the kinematics of dwarf galaxies. And dwarfs sort of fit the bill on everything. They have low backgrounds, they have small angular resolutions in the sky, and we have information corresponding to the dark matter column density and the velocity dispersion of the stars in these objects. So this is what we're going to look at for our test. Before I jump into it, I want to clear up some potential misconceptions. If you have worked or know anything about the WIMP indirect detection search, WIMP indirect detection searches, you might think there are some generic rules that can be immediately applied from your knowledge there to the field of axion decay, and there's a few small misconceptions that I wanted to clear up. The first is that some dwarf spheroids are always better targets. If you're looking for dark matter annihilation, the largest signal is the one that's going to have the largest J factor. So you want the largest density squared, the integration over the density squared. This isn't actually generically true here. We have an angular integration which is now mass dependent. So if I want to probe a 10 to the minus 5 eV axion, I might want a different target than a 10 to the minus 4 eV axion. This is just something to keep in mind. For gamma ray searches, higher efficiency is almost always achieved with a stacked analysis. This is because something like Fermilab has a massive field of view. It sees a fifth of the sky at any given time. But with radio telescopes, you have a tiny, tiny field of view. You need to choose whether you want to point at Willman 1, Reticulum 2, or the galactic center. And if you need to choose that, you want to point at the best object. Unless you want to remove systematics, in which case you want to point at the best objects and then do a stacked analysis. But in general, doing a stacked analysis will remove or reduce your overall sensitivity unless you have systematic issues. And so the small field of view means no dwarf spheroids or free. And in general, people have this notion that there's large uncertainties in the astrophysical factor, and that is true for a lot of web searches as we've heard today. But we're not interested in the J factor. We're interested in only the density. And the differences in the density are significantly less than the interested in the J factor. So many of the dwarfs we're going to talk about are approximately equivalent. I may mention a dwarf like Willman 1 as being a good target. People have noted that Willman 1 has many problems, and most notably, it looks to be tidally disrupted. And so this may not be an accurate reflection of the dark matter density from the derivations that people have done. But it doesn't really matter because there are many, many targets which have the same sensitivity. All right, since I'm running out of time, I'm going to skip this slide. It doesn't really matter. It's just a depiction of various strengths of the integration of the dark matter column density divided by the velocity dispersion for various dwarfs. And we can jump to what you can get with SKA sensitivity with 100 hours of observation. I plotted the axion to photon coupling here on the y-axis, and again the axion mass on the x-axis. You can see the conventional loaded KSBZ and DFSZ lines here down here, as well as projections for altitude and Yoxo. And what you see is that SKA mid contain a significant sensitivity, even probing a small amount of the QCD axion band with 100 hours of observation. So this looks pretty good, looks quite promising. But it's not the end of the story. In general, I didn't want to claim that dwarf galaxies are going to be the best sensitivity. They probably won't. They might give you a good place to start, but there are many, many other environments where you gain and get enhanced flux. So you can do a number of comparisons between the overall dark matter density and the velocity dispersion, including the angular dependence for radio telescopes you want to use for the galactic center, for galaxy clusters. All of these are going to provide you with promising targets. But additionally, we sort of neglected the simulated emission enhancement. And I mentioned earlier that at low frequencies, like you can see on this graph, synchrotron emission, these blue lines, have a much, much larger flux than the CME does. This means the number density enhancement at low frequencies is much larger than you expect from the CME. And you can get a 2 to 3, maybe 3 to 4 order of magnitude enhancement from the simulated emission. So we're working right now on potentially trying to map out the synchrotron emission distribution and make some reasonable assumptions about the spatial distribution to see what the effect of this enhancement can be in the galactic center. All right. I'm also discussing we can exploit existing radio telescope data. Telescopes like Arecibo have already done analysis for the last 15 to 20 years, for example, on stacked galaxy clusters with over 50,000 different observations. These spectrum exist. They have all the features we want. The only downside of these features is that they're centered in a very, very narrow frequency band. So we can't get that full frequency that we want with SKA. We may only be able to probe a factor of 2 in axion mass between 10 to the minus 4 and 2 times 10 to the minus 4. There's also other things we've learned from web searches. For example, we have shown in web searches that you get very, very powerful constraints by doing cross-correlation power spectrum studies. You could try to cross-correlate the signal from axion decay with large-scale structured tracers like galaxy catalogs. And this could potentially provide a promising probe and confirmation of the axion line. So this is something we've also been discussing, and it's also something that was investigated by Mark Kaminkowski, one of his collaborators, for H1 mapping experiments. Alright, so the take-home messages are that radio telescopes are ideally placed to probe the QCD axion mass range. On galactic scales, as I said, axion decay is far more important than the conventional non-resonant axion photon conversion. And they're very complementary to conventional direct axion searches like haloscopes and helioscopes. They provide very additional indirect detection constraint, which is very complementary in these ways. Looking forward, there's many other signatures and targets and telescopes to look for. We would like to try to do this with real data. We'd like to try to identify what the most promising signatures are. And we'd like to see if we can exploit the stimulated emission in some clever way to see if we can get an extra enhancement and boost. So I think that's all I have.
Thank you very much, Sam, for this very interesting and clear talk. Are there questions?
So you haven't mentioned any backgrounds. Should we worry about anything?
I'm glad you asked this question. I love this question. Usually people worry about synchrotron is a background, by the way. And usually people worry about synchrotron. And they say it's a huge orders of magnitude over whatever you want your signal. But as I told you, my signal scales like the number density of my background. So signal to noise is now scaling like the square root of your background. So actually, when I include synchrotron emission in my background modeling, I should get an enhanced signal. It's actually quite beneficial. It's quite nice. Now, the issue would be, maybe for cross-correlation studies, it's possible that your synchrotron emission is coming from foreground emission of the galaxy, and you're trying to cross-correlate with something in the background. Now we don't have the stimulated emission enhancement in the signal to noise because you're not having overlap between the number density of photons which are causing the noise and the ones that are producing the signal. That could be a concern, but that's for something in the future. Thank you.
How do the bounds from SKA, how are those compared to the bounds from in labs?
I mean, so...
Like CAST?
So CAST is up here on the helioscope bounds. So helioscopes, we have haloscopes, or these light blue. This is ADMX in these experiments. And then you have ALPS2 and YAPSO projections. So it seems to be very competitive with some of these probes. As you saw yesterday in Ben Safdie's talk, his indirect searches are actually much stronger than this. In principle, the pulsar searches could be a far more promising tool for radio telescopes. But nevertheless, if you were to detect a axion photon conversion line from the pulsar search, and you were to detect at half the energy a decay line in a different environment, that could be a very convincing astrophysical signal.
And where's the place where the helioscopes are starting to probe the QCD?
Helioscopes up here. I mean, so the QCD axion band doesn't show up low right here. This is the axion band as taken by Luca. So you can see this green line would extend right up here to 10 to the minus 2 maybe, and helioscopes like CAST go across the edge, almost horizontally. Yeah.
Oh, wow.
Yeah, no.
Wonderful talk. No, I just want, I have one question. So, what you're saying is that you got this unanswered signal coming from something like radio wavelength photons annihilating to an axion, right?
No, axion comes from photons.
Yeah, sure. But then you have these unanswered factor by simulated emission.
Exactly.
Yeah. Then my question is, you are assuming you are considering CMB for
yes.
the emission, right?
Yes.
But perhaps it's a naive question, but shouldn't you need a thermalized photon to have something like this? And actually, CMB is not really thermal distribution. I mean, it's just inheriting the distribution from last scattering, but it's not in thermal equilibrium. So, in Boltzmann equation, you assume that this is in thermal equilibrium.
It's something I want to think about, but I don't think this matters. I've done 2 different calculations in 2 entirely different methodologies, and they both led to the exact same conclusion. And I don't think it needs to be thermalized.
What is the second methodology?
The second one is an atomic physics calculation, which is why I didn't present it at a particle physics conference. But we can talk about it after, but I don't believe that it needs to be thermalized. It's a good question, but yeah.
And
The uncertainty that I'm showing right here is coming from the uncertainty, the D factor. So in general, people have worked looking at the stellar kinematics of dwarf galaxies and using this to infer the dark matter column density, as well as, again, I'm assuming, for example, the dark matter velocity distribution dispersion follows that of the stellar contribution. So this band is directly translated almost into my astrophysical contribution on this band.
Hi.
You're on this paper, I'm not sure you
I just wanted to add a comment to Eduardo. I mean, you can write down the equation anyway with a function distribution. I mean, you don't care about thermalization or not, in general, right? And if you, why not? I mean, what do you mean?
We can discuss it after, but I don't think this is a relevant feature. It's a good question, but I don't think this is important.
So I think that there are no more urgent questions, so we thank all the speakers of this session.